I can change to whatever port number I like. What if let's say I want 11445? I can change to whatever. Then I'm going to go back to Mozilla. Okay. Then I'm going to try and contact my server. HTTP, localhost again. Set 1445. Then 159.334.html. So there you go. Then we can look at the cache again. So I'm going to run about :cache. Then there you can see. So it has stored, related to this website. So I've got some image of a sheep there. So you can see the sheep, that JPEG. You can see the HTML 159.334.html. Now I'm going to modify this program. Okay, let me just clear the cache again. Tools, options, tools, clear recent history, clear everything, clear now. Then I'm going to just double check. Cache 00. Then I'm going to go back to my program. This time, I'm going to instruct the web browser, do not cache. Okay? So how do we do that? It's very simple. You'll find that we just need to add a few more details here. Where is it? Our current topic. Cache control, no store. Please do not store. Okay? Do not store it in your hard drive. But the browser, of course, will have to store it in its memory. Okay, so it can still be hacked. You can see. So what a hacker might want to do, check the disk drive, check the memory, if there's any cookie that can be used later on for attack. Okay. In simplest terms. So I'm going to close this, okay, save, compile, then I'm going to run my server again. Let's use another port number. Let's say 2334. Okay. So we can change to whatever port number for as long as it's available. So 2334. That's the port number. And you can see all the details, all the objects were transmitted. Okay. Now we can check the web cache this time. You can check if the browser followed the instructions. Okay. So previously you can see 00. Okay. This is the disk cache. Okay. You can see that the disk cache contains 2 entries, okay? But these entries are just links, not really the actual HTML. Okay? You don't see the ship anymore. Whereas in the memory cache, of course, all these objects are still there. That's why attackers might want to try and grab those objects from the memory. So we can see that we can, for as long as we conform to the protocol definition, we can actually exchange information with a web browser. Okay? You can come up with your own web server. And if you want to perform encryption, that is your own encryption scheme. Nobody can, can just hack it. Okay? I'm hoping to get to the point where we can look at the programming part. Let's just briefly have a look at HTTP2. So far we've been looking at HTTP version 1.1. That was released in 1999. And you can see there's a big jump 16 years later, HTTP2. And this HTTP2 is a product of the combined effort of engineers and scientists from Google and Mozilla, if I'm not mistaken, but mostly from Google. And it is a product of an improved version of their HTTP compatible protocol, Speedy, that was running experimental for time. Eventually, Speedy became HTTP2 after some refinements. And if you might be wondering how many websites around the globe is using HTTP2, so far, only 33.9%. So it's going to be deployed slowly. And what is it doing? It is able to reduce the perceived latency. So if you're trying to download the web page using HTTP2, it's going to be faster. Now why? First, we saw that the header fields are very descriptive, very long, like if none match, if modified since. These are strings. So what they did, compress these header fields. So the size is drastically reduced. If you're able to reduce the size of the packet, that will speed up the communication session. And another improvement is that instead of making use of multiple concurrent connections, because here what we are seeing here is just one connection. But typically, to speed up the connection, the exchange of packets between the server and the browser, you can have as many ports here and as many ports in the server browser side, okay, that can connect to the server at the same time. Typically, it's set to about 6, okay, per server, or about 8 per server. And to improve the transfer of these objects, HTTP2 allows concurrent connections within the same TCP connection. So it's a completely new strategy because it's using header compression and what else? It also allows the client to indicate to the server, out of these 10 objects, this is the top priority. So I want to download this first. Instead of downloading each and every object one by one sequentially, it can be ordered. And also, HTTP2 allows the server to indicate, you should download this one first because this is important. So this server push allows the transfer of resources without the client requesting for them explicitly. Okay? And what's good about HTTP2 is that it does not obsolete the syntax of HTTP 1.1. Otherwise, imagine everything we just talked about will be completely wiped out. So it's very good. It's downward compatible. We're not going to lose, in the many years to come, we will still be using the same syntax and the semantics remain unchanged. That was 2015. It's interesting, we now have HTTP 3 as well. So HTTP 2 is not even widely deployed yet, but scientists from Google is already proposing HTTP 3. And interestingly, this one has been approved just last year. And what's more interesting is that HTTP will no longer make use of TCP. It's going to make use of, where's TCP? This is TCP. This is TCP socket. TCP socket. In their proposal, they want to use a QUIC protocol. They call it QUIC. And if you look at QUIC, interestingly, QUIC is an experimental transport layer protocol, okay, contributed by Google. And what they say is that QUIC is implemented using UDP. It's fascinating. Okay? It's using UDP that is multiplexed, okay? Using multiplexed UDP. Okay? So that's what's going to come in the future. Okay? So this is an upcoming major revision of HTTP. So for references, you can have a look at these. Of course, from the Internet Engineering Task Force, I've got the book. And it's interesting to look at Mozilla as well, Mozilla developers website. Mozilla allows, shares their API. So next, we're going to start talking about programming. I thought we can talk about this a bit earlier. Part 1, we're going to talk about TCP. And we know there are only two, TCP, UDP, and out of the two you can come up with your own protocol, like quick. You can develop whatever you want. We're going to talk about IPv4 and IPv6. Cross-platform, runs in Linux, Mac, or Windows, and actually just see. You can convert them later on into classes, so you can have your own network engine. That's what I started doing. So you'll be able to learn how to build Linux server applications, or even peer-to-peer if you'll make a big effort. In order to write programs that make use of sockets, you need to get acquainted with the different functions available, and then you will find that there are so many predefined structures, constants, error codes. So remember that we are borrowing the API from the operating system. What's important is that all operating systems, be it Linux, Windows, Mac, OS, they need to use, they need to comply with the definition of this API. So each operating system implements this socket library. There will be some very slight differences. What's also important is that we need to know which function to call first, followed by the next. If you reorder them, it's not going to work. So we are literally learning how to use the API. Okay? And I'm sorry the names they use are sometimes a bit confusing. We know this already. The socket lies in between the application layer and the transport layer. It can be TCP, it can be UDP. It is controlled by the operating system, so that the API is implemented by the operating system itself. And we're just calling these functions. So it serves as a gateway to the outside world, both for sending and receiving. And we have two types of sockets. So we got TCP, which is string oriented, and we have the UDP, which is called a datagram socket, which is unreliable. Remember, unreliable datagram, but in the future we will be using that for HTTP version 3. That's interesting. We will be looking at the cross-platform implementation, but I told the class, I need you to submit the Windows compatible. You can write the cross-platform and you can submit it. Okay? But you need to write so many codes. You need to consider if it's Linux, if it's Windows, if it's Mac, you need to have different compiler directives. And we have starter codes to help you learn these things. We will be using WinSock version 2 from Windows. Okay? But I'm going to talk about the cross-platform as well. Okay. First, TCP. Okay. Within the operating system, every time you allocate a socket, it's going to allocate buffers and state variables. Then this is what we've learned already. If you're going to write a TCP server, it has to have a listening socket. See? The minimum sockets required to implement a TCP server is equal to 2. You have a listening socket, okay? And then later on, another extra socket exclusively for a client. So if a client arrives, it has to create a socket, and it has to connect to that specific IP address and port number of that server. Once detected, the server will generate a new socket. It's going to create a new socket. This socket allows for bidirectional exchange of messages. The client can send, and the server can also send across the same link. Once the client bids goodbye, this connection will be destroyed, as well as the resources allocated for these sockets. So we're familiar with many of these details now. We need to identify the server by means of its IP address and port number combination. And what we also want to remember is that once the connection has been established, as if there's a pipe between the two distributed applications. Okay. Why do you want to think about it like that? Okay. TCP provides for reliable data transfer. If, for instance, you're transmitting some packet here, you know that the connection is not a direct connection like that. It's going to go through several routers, right? Maybe you're trying to contact a server in the US. Maybe 30 hops. And the packet might get corrupted somewhere along the way. Or it can also be dropped. Okay? But since this TCP socket is implemented by the operating system, and it's also implementing reliable data transfer, it may have to, typically it's going to retransmit several chunks of that packet just to make sure that it arrives for sure at the destination point. So let's look at this very simple client-server application. We will start looking at the code. Let's say we have a program where the client reads a line from a standard input. Maybe I'm going to do a quick demo so we can easily see. Okay. So hopefully I will have enough time. I just want to point out, okay, for this session, you will find that the codes are available in our stream website. Okay. What I'm going to demonstrate is the same codes that you will find here. We've got TCP server client cross-platform. Okay. You can download it already. Okay. And I'm going to run the client and the server. This is going to be our very first program to examine. Socket programming, this is the server, and I also need the client. Both of the programs contain a make file. Let me just go to the others. This is the server. I've compiled it already. I'm going to open a window for the server. And I'm going to run the server first. Server Windows followed by some port number, say 3120, whatever. Then I'm going to run the client. Put it on the left. The name of the client is server. Oh, that's not the client. Talking about this. The name of the client is client Windows. Oh, this is not the cross-platform, sorry. But you have the cross-platform. I'm going to make available the cross-platform in just the Windows-based. So it's not going to be confusing. To communicate to the server, I need to specify the host name. The host name is inside my machine, so localhost, followed by the port number 3123. Then you can see that they will communicate. If I type here hello, it's going to be received by the server, and it's going to modify it a bit, and then it's going to transmit it back to the client. So the server here generated the message. The client typed hello, followed by how many bytes. Then here, it is received by the client. The client typed hello, 5 bytes. So it's just an echo, type of program. And quickly, before we dismiss, just so that we will end up a bit smoothly. How is it going to look like? Let me talk about it briefly in 2 minutes. The server needs to create a socket, and then that socket needs to be bound on an IP address and a port number. That will be our welcome socket. Okay. It's going to start listening for an incoming client. Once a client arrives, okay, we're talking about a client. with its own socket. The client needs to connect to the server exactly using the server's host name and port number. And here we can see that the client has its own socket. This is going to help establish a TCP connection between them once the accept function is able to receive that connection. Then we can see here that once the client has been accepted, another connection socket, the second socket, is created. And the communication between the client and the server will be done by that connection socket. When the client bids goodbye, this connection socket will be closed, but the welcome socket is still open. So next meeting, we're going to look at the codes, the actual codes, and going to look at the functions. We're going to talk about UDP as well, and what else? I did some demo already. We're going to talk about IPv6 a bit, and the syntax, the actual program starting from the header files up to what's going on inside, compiling, and so on and so forth. So that will be that's the plan. You can find these slides already in our website, but today is already 11:30.